Okay, let's move on and talk about subspaces. For any vector space, a subspace is a subset of that vector space that is itself a vector space under the inherited operation. What does inherited operation mean? It means for the big vector space there's a plus and a scalar multiplication, and in the subset you have to use the same plus and the same scalar multiplication. Alright, if that's not clear, we'll make it clear with some examples. Let's just get it to work. Right. Now, any vector space has a trivial subspace, which is the zero vector. We've already talked about how the zero vector is a vector space in itself. At the opposite extreme, any vector space is itself a subspace. All right. These two are called improper subspaces. The other subspaces are proper. All right, here's an example. Consider the vector space R2. You can think of that as the plane, or vectors with two components. And think of the line y equals 2x. Now, of course, the line y equals 2x is contained in R2. You draw the picture here. If you have a line there and line here. And the line y equals 2x, well, it's going to have slope 2, so it looks something like this. Okay, whoops, that's not where it's supposed to go. So down here. Okay. All right, now, this is in fact the subspace. The operations as required by the definition above are the ones from R2. We could show it's a vector space by checking all 10 conditions, but the next result gives an easier way. And so let's get to the next result. All right, we'll see that in a minute. Okay, the subspace of M2 by 2. M2 by 2 is the vector space of 2 by 2 matrices. And here's a subset of the set of 2 by 2 matrices. It's the subset that has the first column is AA, second column is BB. All right, so another way of describing this is that both rows are equal. Okay. Now, you could write this set in the following way. This is the span of these two vectors. Now, you think of this as a matrix, but we're also thinking of this set of 2 by 2 matrices as a vector space. So this set S is the span of these two vectors in the vector space here. Okay. In fact, you can see that this vector space S here is the span of this vector in R2. Now, what do I mean by span? I mean all linear combinations of this vector. These are all linear combinations of these two vectors. Okay. All right, now this is not a subspace of R3. Now, why is that? Well, one condition it violates is not closed under addition. If you take two elements of T, that's not necessarily another element of T. So you can check that these two elements of T are not contained in T. Right, that's a little exercise. Also, you can notice that the zero vector is not in this set, so it couldn't possibly be a vector space, because any vector space has to have the zero vector. Right, so here's the result that we referred to earlier. In order to show that a subset is a subspace, you only need to show a couple of things. Right, so for a non-empty subset S of a vector space, under the inherited operations, the following are equivalent statements. S is a subspace. S is closed under linear combinations of pairs of vectors. And S is closed under linear combinations of any number of vectors. Okay, so let me unpack this. What this is saying is that these three statements are equivalent statements. S is a subspace if and only if it's closed under linear combinations of pairs of vectors. Also, S is a subspace if and only if it's closed under linear combinations of any number of vectors. So certainly you can see that if it's closed under any number of linear combinations, it's also closed under pairs of under linear combinations of pairs, but in fact all of these statements are equivalent. Now notice that we had back here that in fact this set S was the set of all linear combinations of this vector. Now since there's only one vector of this vector 1, 2, so since there's only one vector, the only linear combinations are scalar multiples. In the same way, the set S here was the set of all linear combinations of these two vectors here. So you can see the close relationship between subspace and linear combination. So this unpacks the equivalence of these three. We have 1 is true implies 2 is true, 2 implies 1 is true, and so on. Right. Now we can prove all three of these are equivalent if we can show that 1 implies 3, 3 implies 2, and 2 implies 1. This also shows, for instance, that 2 implies 3, because if 2 implies 1 and 1 implies 3, then certainly 2 implies 3. You could call that the transitive property. Okay? All right, now this strategy is suggested by the observation that 1 implies 3 and 3 implies 2 are easy. All right, why is 1 implies 3 easy? Well, if S is a subspace, it has to be closed under addition, and it has to be closed under scalar multiplication. So it has to be closed under linear combination and under any possible linear combination. So that's where we get 1 implies 3. 3 implies 2 because 2 is a special case of 3. 3 says arbitrary linear combinations. 2 says linear combinations of pairs of vectors. Right? So the only thing that we need to do, that's left to do, is show that 2 implies 1. In other words, if we have a subset of a vector space that is closed under linear combinations of pairs of vectors, then that subset is a vector space. So as long as we can guarantee that the linear combination of two vectors in S is also in S, then we know S is a subspace. That's a good thing to know, because that's only one thing to check instead of 10 things. Right, so let's go to the proof. So we're assuming that S is a non-empty subset that's closed under linear combinations of pairs of vectors. We will show that S is a vector space by checking the conditions. Okay, the vector space definition has 5 conditions on addition. First, for closure under addition, if S1 and S2 are in S, then S1 plus S2 is in S, because this is a special case of linear combination. Okay. Second, for any S1 and S2, because addition is inherited from V, the sum S1 plus S2 in S is equal to the sum S1 plus S2 in V. And that equals the sum S2 plus S1 in V. In other words, the same proof, the fact that you prove it for V also makes it hold for S, because S is a subset of V. The argument for the third condition, well, let me skip back to these conditions so you can see what I'm talking about. So this conditions 2 and 3, all we're saying here is that if this is true for all vectors in the larger set V, it's also true for all vectors in the smaller set S. So that's where 2 and 3 come from. In fact, you'll use the same proof to show 7, 8, and 9, and 10, that these 4 are also true, because they hold for the larger set V, they'll also hold for the smaller set S. Okay, so we've got 1, 2, 3, 4, 5, 6, 7 down, 3 to go. So what remains to show is that the 0 vector is in S, the additive inverse is in S, and V is closed under scalar multiplication. So we need to show those 3 things. So let's go back and see how we can show that. That's not it. Let's see. Okay. All right, so consider the zero vector of V and note the closure of S under linear combinations of pairs of vectors gives that 0 times S plus 0 times S equals 0 is an element of S. Okay, so in other words, we can express 0 as a linear combination of vectors in S, so that means that 0 itself must be in S. Okay, the fifth condition is satisfied because for any S, closure under linear combinations of pairs of vectors shows that 0 times 0 plus minus 1 times S is in S. And this is the additive inverse of S. That's what we proved in one of the previous lemmas that we showed, that the inverse of S is minus 1 times S. Okay, so that gives us all the conditions that we need. All right, so the condition for scalar multiplication is similar. So that gives us all the conditions we need, and that shows that if we can show a subset of a vector space is closed under linear combination, then that subset is a subspace. Okay, so let's think about this. The vector space of quadratic polynomials, which we saw before, has a subspace made up of linear polynomials. So this is polynomials with an x squared term. This is a subset with polynomials that doesn't have an x squared term. Now, it's pretty clear that if I take any linear combination of linear polynomials, it's still a linear polynomial. So L is a subset of P2 that is closed under linear combination. It follows that L is a subspace of P2. Right? Okay. Another example is the set of quadratic polynomials having 3 equal coefficients. Okay. You can do the same sort of argument to show that this is certainly a subset of P2, and linear combination is also in the same set. Therefore, this is a subspace of P2. Okay. Each of the examples of subspaces parametrizes the description. Okay. In other words, the subset is described in terms of parameters. Okay. Right, now here, this is a set. This set is a plane inside of R3. Right. Actually, this is the set of points in R3 that are perpendicular to the vector 2, minus 1, 1. If you think about it, all of the vectors that are perpendicular to a given vector is a plane. Let me just draw a simple picture here. If I have a vector here, I should draw an arrow, but I think you can see what I mean here. And then if I draw a plane, the set of all vectors perpendicular to that vector, that's perpendicular. This one is going to be perpendicular. If I drew it in here, if I went straight out of the page, that would be perpendicular to this. If you drew all of those vectors that are perpendicular to this given red vector, that would be a plane. Right. Now, we could verify that this is a subspace by checking that it's closed under linear combinations. Okay. That's easier if we first parameterize this linear system by using the free variables. In fact, this set P can be rewritten. This is a solution of a homogeneous equation. We can rewrite it in terms of its free variables. Okay. Now, members of P are described as linear combinations of these two vectors. Now, if you take linear combinations of vectors in P, that's going to be a linear combination of linear combinations, which we already showed gives a linear combination. Okay, so that shows that P is closed under linear combination. Automatically, P is a subspace of R3. All right, here we have the span. I used this word earlier, but here's the formal definition. The span or linear closure of a non-empty subset S of a vector space is a set of all linear combinations of vectors from that set. All right, so if we have different vectors S1 through Sn in the set S, we take linear combination. We take all possible linear combinations of all possible sets of vectors in S, and that gives us the span of S. The span of the empty subset of a vector space is its trivial subspace. No notation for the span is completely standard, so we can just say span of S, so it's fine. Okay. All right, so here's an example. Inside the vector space of all two wide row vectors, the span of this one element set is the set of vectors that can be written in this form. It's the linear combinations of 1, 2, since there's only one vector, is just scalar multiples of 1, 2. Now we saw this before, and we already know that this is a subspace of R2. S is a subspace of R2. All right, here's another subset of R3. S is these two vectors. Now we can take the span of these is going to be all arbitrary linear combinations of these two vectors. Okay, any vector in the xy plane is a member of the span because such vector is a combination of these two. You can actually set that up as a system of linear equations. If you have any vector x, y, 0, you can write x, y, 0 as a linear combination of these two vectors. Vectors not in the xy plane are not in the span. It's clear that if I take a linear combination of these two vectors, the third component is always 0. There's no way to make it non-zero. So if I have a vector not in the xy plane that doesn't have third component 0, there's no way that it could possibly be in the span. Okay, in a vector space, the span of any subset is a subspace. I think that that's kind of indicated by the examples. Okay. All right, so if the subset S is empty, by definition, its span is the trivial subspace. Okay. If S is not empty, then by lemma 2.9, we need only check that the span is closed under linear combinations of pairs of elements. Okay. For a pair of vectors from that span, here we have any element in the span is a linear combination of vectors. Okay. So that means, but if I take any linear combination of V and W, that's also a linear combination. So that's also in the span by definition. So again, we're using this fact that linear combination of linear combinations is also a linear combination. Each vector in the span is a linear combination. If I take the linear combination of 2, it's still a linear combination. So we get something that's a linear combination, which tells us that this subset is a subspace. And that's it.